Hello, everyone. It is a pleasure and an honor to be here with all of you today, even if virtually. I'm deeply grateful to Kerala School of Mathematics and especially to its director, Professor Kullan Chakraborty, for the invitation, for organizing this event, and most of all for this terrific initiative at a time when many things are on hold. I hope that all the students and junior researchers at KSOM will find this conference engaging and productive. Today, I would like to talk about a circle of ideas that I have found intriguing for a number of years. There are two main ingredients in this study: a set of directions and an operator that is governed by this set of directions. It is natural to expect that the underlying set of directions should play a role in the behavior of the operators, but the challenge is to find out how. Here is a plan for my talk. I will start out by describing what I mean by an operator with directions and provide some examples. This will be followed by a discussion about why these operators are important and why we study them. The literature on this is vast. I will try to give an overview of the currently known results that are most closely related to our study. Finally, if time permits, I hope to give you an idea of some of the proof techniques. Let capital omega denote a set of directions in d-dimensional Euclidean space where d is at least 2. In other words, capital omega is a subset of the unit sphere SD-1 in Rd. In the diagram, the green globe is the unit sphere in 3D, and the red area denotes a possible choice of capital omega on the sphere. A directional operator takes a d-variate function as f as input and then uses omega in some way to produce a function g as output. Of course, there are any number of ways in which capital omega can be used in the construction of the output function g. Let me give two examples, which will also set the stage for the remainder of the talk. Let f be a well-behaved, smooth input function in d real variables. Given a function, little x, given a point, little x, in Rd, consider all possible line segments centered at x and pointing in some direction, little omega, in capital omega. Take the average of absolute value of f over all such line segments. The output function g evaluated at x is the supremum of the largest of these averages. The resulting operator, which we denote by m sub omega, is called the maximal directional average. Let's look at another example. Before I define what this operator is, pick your favorite univariate transform, by which I mean a transformation rule that takes a one variable function phi as input and returns a scalar. Again, there is an infinite range of choices here. A transform, for example, could be the average or the weighted average of the function phi, or it could be phi evaluated at a point. For specificity, I have chosen the Hilbert transform on R, which simply integrates the input function phi with respect to the singular integration kernel 1 over t in the principal value sense. This choice is not entirely random. The Hilbert transform plays a fundamental role in complex analysis, functional analysis, and in Fourier theory. Now, given a nice input function f in d variables and any point x, compute this transform for f restricted to the line passing through x and pointing in some direction little omega of capital Omega. For the Hilbert transform, this means considering the principal value integral of the function f of x plus t omega as a function of t. As before, we look at the largest value of these transforms over omega and call it h sub omega, the maximal directional Hilbert transform. Note that in both of these examples, we have chosen to look at a maximal operator associated with capital Omega. One could, of course, try other ways, such as averaging over the points in capital Omega rather than looking at the largest value. The maximal operator, however, dominates, in other words, is pointwise larger than all such averages, and as a result, captures the worst case scenario. With these two operators set up, we run into some natural questions. Where do such operators occur in practice? What properties of these operators are relevant for applications? Are these operators good or bad? And how does one measure the behavior of an operator anyway? For us, an operator is good if it is bounded on certain function spaces, such as the Lebesgue spaces LP. Being bounded on an LP space means that if you feed in an LP integrable function f into the operator, the output function g remains in the same space. Thus, the operator rule does not allow something ill-behaved to be constructed out of a nice function. In other words, the behavior of the output function is no worse than the input. Finally, how does the geometry of capital Omega drive the behavior of m omega and h omega? Just from a superficial inspection, we see that as omega gets larger, we take supremum over larger and larger sets. And as a result, both m omega and h omega increase pointwise as omega increases. It seems possible that at some point, the operators may become unbounded for some large omega, but is that truly the case? Before we head out to explore these avenues, let's take a brief pause and see if you have any questions. In this segment of the talk, we will address the question, why should we study directional maximal operators? Here is a brief sample of mathematical applications where directional operators play an important role. In the fields of geometric measure theory and combinatorics, directional operators are perhaps most well known in the study of sets containing many lines, for example, the extraordinary Kakaya-Besikowitz set and its variants. Are the primary tools in many central and often open problems in harmonic analysis. They arise, for example, in Pfefferman's counterexample for the ball multiplier, in Bochner-Ries means and Fourier restriction conjectures, and in Stein's conjecture for the Hilbert transform along Lipschitz vector fields. They appear in differentiation theorems, especially over geometric objects that have orientations like lines, rectangles, and ellipses. Each one of the items on this list is a research direction in itself. For the purpose of this talk, I will restrict myself only to the first one on the list, the Kakaya-Bešičković set. In the year 1917, the following problem posed by the Japanese mathematician Soichi Kakaya appeared in the Tohoku Journal of Mathematics. What is the least area of a convex set in the plane within which a needle of unit length can turn through an angle of 360 degrees without any part of the needle ever leaving the set? The question was solved shortly thereafter by Paul, who showed that the answer is an equilateral triangle of unit height. But Paul himself asked a follow-up question. What if the set is not required to be convex? Based on earlier work by Kubota, he showed that the deltoid beats the triangle in terms of area. But is it really the smallest? Around 1919-1920, the Russian mathematician Abraham Samuelovich Bešičković constructed such a set in the plane with Lebesgue measure 0. His construction permits an easy generalization to higher dimensions. For the purpose of this talk, we will call a set that contains a unit line segment in every direction a Kakaya-Bešičković set, or a KB set for short. The history of the KB set is a fascinating one. Bešičković received his PhD from St. Petersburg under the supervision of the famous probabilist Markov. Shortly thereafter, he accepted an academic position and moved to the city of Perm, deep in the Ural Mountains. At that time, due to political unrest in Russia, the university at Perm was completely isolated from the rest of the mathematical world, as a result of which Bešičković had no knowledge of Kakaya's question. Legend has it that his original goal was to pursue mathematical logic, but the library at Perm did not have enough references on the subject. They did, however, have a great collection in analysis, and in fact, it was a question about multivariate Riemann integration, unrelated to the Kakaya problem, that led Bešičković to discover the KB set. It was much later, after he moved to the UK, that he found out about the Kakaya problem from Paul and republished his work in the 1940s. Let us ask a delta-thickened formulation of Kakaya's question. If we thicken by delta a set which contains a unit line segment in every direction, what is the smallest area of such a set? In this formulation, a unit line segment after thickening becomes a 1 by delta rectangle. Such a rectangle containing unit lines, the segments, pointing in a direction of angular range roughly delta. Can one arrange many such rectangles to cover minimal area, but also cover the entire angular range of 2 pi? Besikovich's original construction has been modified in many ways. Let us focus on the statement that is most pertinent to us. It says the following. Let us fix a positive epsilon, arbitrarily small. Then one can find an integer, capital N, and a collection of rectangles R1 through Rn, each of length 1 and width 1 over n, oriented in distinct 1 over n separated directions, such that their combined size is less than the prescribed epsilon. This means that the union of the rectangles Rj is a Kakaya-Besikowicz set of Lebesgue measure less than epsilon. At the same time, these rectangles can be arranged in such a way that their reaches are disjoint. What is the reach of a rectangle? Let's refer back to the diagram. Suppose that capital R is one of the rectangles Rj, say the black one oriented horizontally. It has length 1, width 1 over n. If we slide R along its long direction by 2 units, we get to another rectangle of the same dimension and orientation. We call this translated rectangle R star the reach of R. The statement of the existence of the Kakaya-Besikowicz set says that not only is it possible to ensure that the rectangles Rj have a lot of overlap so that their total area is less than epsilon, if you slide them 2 units along their long axes, their reach rectangles spring apart and become disjoint. This is all very good, but what does this have to do with directional maximal operators? It turns out that the existence of the Kakaya-Besikowicz set has a rather dramatic consequence for the maximal directional average m omega, where omega is the set of all directions in the plane. More precisely, the existence of the KB set dictates that m sub S1, where S1 is the unit circle, is unbounded on all the Lebesgue spaces LP for p in 1 to infinity, including 1 but excluding infinity. How can we see this? To prove the unboundedness of an operator, the idea is to construct a sequence of LP normalized test functions f, such that the LP norm of the maximal operator applied to f gets progressively larger. So to that end, let's fix a positive epsilon, arbitrarily small, and let capital E, given by the union of the rectangles Rj, denote the Kakaya-Besikowicz set of measure less than epsilon. The test function of our choice is the characteristic function of E. This means that the LP norm of f raised to the power of p is just the measure of E, which is less than epsilon by construction. On the other hand, we claim that the maximal operator m sub S1 applied to f is bounded from below by a fixed constant, say 1 over 10, on the set E star, which is the union of the reach rectangles Rj star. Let's take this pointwise lower bound on faith just for the time being. Since E star has Lebesgue measure 1, this means that the LP norm of the maximal function is bounded below by a fixed constant as well. Thus, the ratio of the pth power of the LP norms of the output and the input functions is bounded from below by a constant multiple of epsilon inverse, which blows up as epsilon goes to 0. So the only part of this argument that requires justification is the pointwise lower bound of the maximal function on E star. Where does this come from? To see this, pick a point x in E star, which must therefore lie in Rj star for some j. Let capital R denote the tenfold dilate of Rj star, which means that capital R has the same center as Rj star, but 10 times its length. Thus, capital R must contain Rj, and the test function is 1 there. Therefore, the average of the test function on capital R picks up a certain amount of mass just by virtue of containing Rj. And when you compare the length of Rj with the length of R, that's where this fixed constant lower bound comes from. Let's pause for a moment to summarize what we have just found. On one hand, the KB set by definition contains many lines and hence cannot be too small, right? But we have just seen that it could have Lebesgue measure 0 and hence is sparse in this sense. So, how large is it? What this suggests is that perhaps Lebesgue is too crude a measure for the size of the KB set. After all, a line and a point in the plane both have Lebesgue measure 0, but they are certainly not of the same size. A line has dimension 1, whereas a point has dimension 0. What's the dimension of the KB set? Now, there are many distinct notions of dimension in geometric measure theory. For this talk, let us just focus on the simplest one. Given a Borel set, capital F, cover F by balls of radius epsilon in an optimal way. If it takes roughly epsilon to the minus alpha many epsilon balls to cover F as epsilon goes to 0, then we say that F has Minkowski dimension alpha. And it's an easy check to find out that according to this definition, the dimension of the Cantor middle third set is log 2 over log 3. With this definition behind us, let us refine our earlier question about the size of the KB set. Suppose that E is a subset of RD that contains a unit line segment in every direction. How small can the dimension of E be? The famous Kakaya conjecture says that any such set must have full Hausdorff and hence Minkowski dimension. In other words, there is no KB set of dimension strictly smaller than D. The Kakaya conjecture is known to be true in dimension D equal to 2. It remains open in all higher dimensions, though not from lack of trying, as you can see from this list. A number of generation leading mathematicians have brought a formidable arsenal of tools to the study of this problem, resulting in incremental progress over the years. The references in pink highlight the state-of-the-art knowledge on this problem as of now, both in the Hausdorff and Minkowski sense. Sometimes I find these numbers difficult to digest in real time, so I decided to show you a diagram where things stand. The diagonal line in black is the holy grail of the conjectured bound. The colored lines show some of the improvements. Finally, to round off this discussion, let us ask the following question. We have seen that the existence of the KB set has implications for certain directional operators. Is the converse also true? Can the study of such operators contribute to the study of KB sets? The answer is yes. The two objects are intricately related. Let us consider a close relative of the maximal directional average, namely the Nikodym maximal function. This is the supremum of F over all tubes of unit length and cross-sectional width delta. The Nikodym maximal conjecture asserts that the maximal operator n delta maps LD of RD to itself with an operator norm that grows sub-polynomially in 1 over delta. It is known that this implies the Kakaya conjecture. More precisely, if you have a fixed alpha here, that would imply a lower bound on the Hausdorff dimension of the KB set. So this closes the circle of dependencies between the size of the set and the property of the directional maximal operator. We will return to the talk again in a couple of minutes, but let's take a short break to see if you have any questions on the material so far.
Yeah, if there are no questions, then we can move forward.
Okay, let's continue. Remember our old friends, M omega and H omega, the maximal directional average and the maximal directional Hilbert transform? This section of my talk will provide an overview of some results, mostly in the planar setting for these operators. I have recorded in this slide some of the notable advances in this area. There are many, as you can see. In the interest of time, I will not go over their individual contributions in this talk, rather report on the current state of knowledge from this combined body of work. In the previous segment of the talk, we have seen a feature of a Kakaya-Besikowicz construction that shows a surprising disparity between the size of certain overlapping rectangles and the size of their reaches. Inspired by that construction, we introduce the following definition. Let capital C be a fixed absolute constant. We say that a direction set omega admits Kakaya type sets if one can find a sequence of delta going to 0 and a collection of delta tubes pointing in the directions of omega such that the ratio of the measures E tilde over E goes to infinity as delta goes to 0. Here, E denotes the union of the delta tubes and E tilde denotes the union of their C-fold dilates. The same proof that we used before to prove unboundedness of M sub S1 then lifts verbatim to show that if omega admits Kakaya type sets, then M omega is unbounded on all the Lebesgue spaces except L infinity. Here are some examples of sets of directions that admit Kakaya type sets. Of course, the full set of directions in the plane, the unit circle, is an obvious choice. Another choice is the set of directions whose angles lie in the Cantor middle third set. This was shown by Bateman and Katz. In joint work with Ed Kroc, we extended this to any Cantor set of positive Hausdorff dimension on a bi-Lipschitz curve in RD. By virtue of our previous discussion, the directional maximal average corresponding to these direction sets are all unbounded. Are there direction sets that do not admit Kakaya type phenomena? It turns out there are, and these too have a long history. The first such example goes back to the work of Nagelstein and Wenger in the late 1970s. The direction set that they found was of geometric type, namely, each vector in the set is parallel to a vector of the form 2 to the power minus JA1 all the way up to 2 to the power of minus JAD, where A1 through AD are distinct positive numbers. Another such set was found by Carberry, and it is the d-fold Cartesian product of the set 2 to the minus j. In both cases, the authors show that the corresponding maximal directional average is LP bounded for all p except 1. And this means that the direction set cannot admit Kakaya type sets. By the way, note that these kinds of geometrically decaying sequences or sets are countable with dimension 0, unlike the Cantor middle third set in the last slide, which has positive Hausdorff dimension log 2 over log 3. Let's summarize the discussion so far. We have seen that some infinite but sparse direction sets omega give rise to M sub omega, whereas certain denser sets do not. This gives rise to a natural question: which property of omega characterizes boundedness of M omega on Lebesgue spaces? The next few slides are given over to answering this question. Of specific importance to this discussion is the notion of lacunary sequences. We say that a sequence xj contained in the unit interval is lacunary if there exists a number x and a fixed constant lambda strictly smaller than 1, such that the distance of xj plus 1 to x is at most lambda times the distance of xj to x. For example, 2 to the power of minus j is lacunary with lambda equals 1/2 and x equal to 0. On the other hand, 1 over j is not lacunary, neither is the reciprocal of any polynomial in j, nor is the set of rationals lacunary for any lambda. Of crucial importance to the study of M omega is a property of direction sets called lacunarity of finite order. In this slide, we will describe roughly what that means. A set is said to be lacunary of order 0 if it is empty or a singleton. A set is lacunary of order 1 if it is a lacunary sequence, as we just described in the last slide. A set is lacunary of order 2 if it consists of a lacunary sequence xj along with a countable collection of lacunary sequences, the jth one converging to xj. For instance, the sequence 2 to the minus j is lacunary of order 1 whereas the collection 2 to the minus j plus 3 to the minus k is lacunary of order 2. Why? If you freeze j and let k go to infinity, you have a lacunary sequence converging to 2 to the minus j, which is itself lacunary. This definition is good for building intuition, but it lacks precision. So let's take another pass at the definition in the next slide. The rigorous definition of lacunarity of finite order proceeds inductively. A set capital E is lacunary of order 0 if it is empty or a singleton. We say that a set E is lacunary of order capital N and constant at most lambda, provided there exists a lacunary sequence capital X with lacunarity constant lambda, such that for any two consecutive elements A and B in X, the subset of E contained in the open interval A to B is lacunary of order 1 less, namely it's in lambda n minus of order n minus 1 and constant lambda. We explain this a bit more using the diagram here for the example 2 to the minus j plus 3 to the minus k. Here capital X is the lacunary sequence half, 1/4, 1/8, and so on. We have plotted some of the points of E that falls within the interstitial spaces generated by capital X. When restricted to each one of these interstitial intervals, capital E is given by a lacunary set of order 1. And this proves more precisely that this E is lacunary of order 2. So, this is the result that we have been working towards. It is the culmination of a combined body of work by several mathematicians, notably Alfonseca, Bateman, and Bateman-Katz. Let capital omega be a set of directions in the plane. Each unit vector in omega can be written as cosine theta sine theta, where theta is the angle between the vector and the horizontal axis. Let us identify omega with the corresponding set of angles, theta, between 0 and pi by 2. The result states that the following three conditions are equivalent. Number 1, omega admits Kakaya type sets. Number 2, the angle set theta is not lacunary of any finite order. Number 3, the directional maximal average m omega is unbounded on the Lebesgue spaces LP of R2 for all p, including 1 and excluding infinity. I like this result very much. It ties together a number of concepts from different areas. Admission of Kakaya type sets is a measure theoretic property. Finite order lacunarity is a geometric condition. And boundedness of operators and a maximal operator is something we study in harmonic and functional analysis. It seems incredible that all these criteria should contain the same mathematical information. Incidentally, there is a curious dichotomy that this result points to. If omega is lacunary of finite order, then m omega is unbounded on all the Lebesgue spaces LP with the exception of p equal to 1. Thus, for example, one cannot have a direction set omega where m omega is bounded for, say, p larger than 3 and unbounded for p less than 3. There is a p-dependent generalization of this result due to higher dimensional generalization due to Parset and Rogers. So far, I have only been focusing on the directional maximal average m omega. I would like to compare and contrast it with our second example, the maximal directional Hilbert transform. This too has been an object of extensive research. I have recorded some of the major contributions to the literature of this operator. I will let you look through this substantial list of work in your own time. But let me draw your attention to some of the results that are known. For example, the work of Demeter and Demeter-Diplinio shows that if a direction set contains capital omega contains capital N many elements, then the LP operator norm of H omega is bounded above by a multiple of log n if P is between 2 and infinity. For certain special direction sets, lower bounds are known. This is the case, for instance, when omega is uniformly distributed. A result that I have found especially intriguing is that of Karagulian from 2007 for P equal to 2 and in dimension 2. Later, in joint work with Isabella Laba and Alessandro Marinelli, we generalized this to all P and all dimensions. The result says that if omega is a direction set consisting of capital N elements, then for any P between 1 and infinity, the LP operator norm of the maximal directional Hilbert transform is bounded from below by square root of log n. This result is startling from a number of perspectives. First of all, it says that there is no infinite direction set for which H omega is Lebesgue bounded. In particular, this means that if omega is an infinite lacunary set, M omega is Lebesgue bounded, but H omega is not. In addition, this lower bound is sharp and attained for lacunary direction sets. Let us turn now to upper bounds for H omega. I would like to state a recent result in this direction with Jongchun Kim. We show that in dimension D, the L2 operator norm of H omega grows like a power of capital N, namely n to the power d minus 1 over 2d, up to an epsilon loss in the exponent. The bound is sharp and attained for uniform direction sets. Incidentally, we also obtain sharp bounds if omega is contained in an algebraic variety, say of dimension m. The main takeaway here is the following: whereas Lebesgue boundedness for infinite direction sets omega was the main direction of research for the directional maximal average m omega, for the maximal directional Hilbert transform H omega, the paramount question is the rate of blow-up as the direction set gets larger, subject to certain geometric conditions. Let's take a quick break for questions before we return to the last segment of the talk.
Yeah, I think if there are no questions, then we can move on.
In the last few minutes that I have left, I plan to give you a very brief overview of the proof techniques used in some of the results that I have quoted today. Let's first consider the work of Bateman that resulted in a planar characterization of the boundedness of the directional maximal average m omega. A crucial ingredient in that study was the representation of the angles associated with the direction set omega as a subtree of a binary tree. What does that mean? The root of the binary tree, which is the 0th level, depicts the interval 0 to 1. At the first level, the root splits into two children. The left child represents the left half interval 0 to 1 half. The other child is the right half interval half to 1. In general, one has 2 to the power of n vertices at the nth level of the tree. Each vertex represents a dyadic interval of the form k over 2 to the n to k plus 1 over 2 to the n. A point x in 0 to 1 is represented using its dyadic expansion, and then the sequence of binary digits 0 and 1 representing x can be traced as an infinite ray moving down the tree. So for example, the point 0 is the one which turns left at every turn. In this language, every slope set in the unit interval is given by a subtree of the binary tree, where a ray belongs to the subtree if and only if the point that it represents lies in the slope set theta or omega. A vertex in a subtree is either splitting or non-splitting. A vertex of script T is splitting if both its children belong to the subtree T, otherwise it is non-splitting. So for example, in this red subtree, this one is a non-splitting vertex, but this one is split. Here I have drawn in red the subtree corresponding to the slope set 2 to the power of minus j, this one, union 0. For each subtree, Bateman defines a quantity called the splitting number of the tree. Given a vertex V of the tree script T, you look at a subtree S of T and pick out the number of splitting vertices on every ray in S. Choose the number of splitting vertices that is smallest among all possible rays of S, and then choose the subtree for which this number is the largest. So this max-min principle results in a quantity called the splitting number of the vertex V, and the largest of these is called the splitting number of the tree. As an example, the red tree here has splitting number 1, since the splitting number of every vertex in the tree is either 0 or 1. So for example, this vertex in the tree has splitting number 0, whereas every vertex on this ray has splitting number 1. So the splitting number of this tree is 1. Bateman's insight was that finite order lacunarity of a slope set omega is equivalent to the tree T omega having finite splitting number. This fact played an instrumental role in the creation of a sequence of random test functions that ultimately led to the unboundedness of M omega, where omega is not lacunary of any finite order. What about the maximal directional Hilbert transform H omega? The next couple slides contain some proof highlights of a joint result with Jongchun Kim. One component of the proof there is an almost orthogonality principle for this operator. More precisely, we decompose the Euclidean space Rd into connected cells Oj, whose union contains omega. And let omega sub j denote the portion of omega that lies in the jth cell Oj. Let Vj be any point in OJ, in other words, a representative of the jth cell, the set O is the collection of all such representatives. The almost orthogonality principle says that the L2 operator norm is bounded above by the norms of H sub O and H sub omega j modulo an auxiliary quantity E that denotes the number of cells OJ that intersect a given hyperplane. Typically, we expect omega j and O to contain fewer elements than omega, and this suggests the divide and conquer strategy based on induction. In order to find an efficient choice of the cells OJ, we appeal to the tool of polynomial partitioning of Euclidean space introduced by Guth and Katz. For any integer capital D and any finite set omega of cardinality capital N, we can find a non-trivial polynomial P in D variables of degree at most capital D, such that the zero set of P decomposes the space into big O of capital D to the D many open connected components, each containing at most big O of capital N divided by capital D to the little d elements of omega. Since omega j contains fewer elements than omega, we can apply induction to estimate the maximal directional Hilbert transform on omega j. And this gives rise to a technical issue. What about the portion of omega j that falls on the cell walls? In principle, this set could be of large cardinality, but the key point is that it is then contained in an algebraic variety of lower dimension, namely the zero set of the partitioning polynomial P. One can then appeal to more refined polynomial partitioning results for algebraic varieties in order to carry the induction forward. Let me close by saying that in today's discussion, we only focused on two directional operators, m omega and h omega. Even within this small sample, we observed a diversity of phenomena in terms of the operators and their dependence on the geometric properties of the direction set omega. There is a large number of directional operators out there, and their behavior is mostly uncharted territory. It would be of great interest to explore what lies there. Thank you for your attention.
Thank you so much, Professor Malabika, for such a wonderful talk. And really that chalks out new areas of research, bridging. Yeah, I'll come, it's not. So, so let's now open the question time. It seems that there are some questions into YouTube. So I'll allow Professor Malabika to respond to these questions.
So Hassan mentioned two questions from the YouTube channel. I couldn't find them on the channel itself. So of these, the first question I didn't understand. The question was, can we construct invariant measures on KB sets? So I'm guessing that by invariant measures, do you under some transformation in ergodic theory? That's my guess. And the answer, if that is the case, then I think the answer is yes. If you are asking about invariance under specific transformations, then I would need to know which transformations you mean. The second question was, is there a relation between m omega and h omega? And the answer is yes. In fact, I refer to this article of Parset and Rogers with higher dimensional P-dependent generalizations. And in that paper that has been published in the American Journal of Mathematics, they obtain a pointwise inequality between these two objects. So they have a pointwise inequality where h omega is bounded from above by m omega modulo some logarithmic factors in n, the cardinality of omega. So that would be the place to look at. Um, so so Hassan just posted another question. One of the way to study fractals is to study interesting self maps of the set and invariant measures associated. What are the interesting self maps and invariant measures on KB sets? So the short answer is I don't know, but if I understand your question correctly, in order for the interesting self maps and invariant measures to make sense, many of these fractals have to be self-similar. In other words, as you zoom into the fractal more and more, there should be the structure of the fractal should remain the same so that one can talk about these self-mappings which have interesting impact on the set. The KB set is not fractal in that sense. It is a sparse set, but it is certainly not self-similar. So in that sense, I do not know if there is a natural invariant measure on the KB set.
Yeah,
So may I ask one question?
sure, sure.
Yeah. So it was a very nice talk. You spoke about two directional operators. What are the other interesting directional operators? Can you name some of them?
Yes. So the directional operators that I introduced today, they were all actually they're valid in all dimensions.
Mm-hmm.
And it is only when I spoke about the characterization that talks about, let's say, the equivalence between finite order lacunarity, the boundedness of the directional average, the admission of Kakaya type sets. This equivalence is only known in the plane. Both the operator m omega and h omega are valid in all dimensions. If you want to go further, go beyond this and look for other operators, so there is an entire zoo out there. For example, you could take a look at Hilbert, instead of looking at Hilbert transform along lines, which is what we did, one could look at a Hilbert transform along curves. So what would that look like? Let's say if you have x in Rd and you pick a curve, let's say just for the sake of argument, t squared, t to the power d. So you look at f of x1 minus t, x2 minus t squared, dot, 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 xd minus t to the power of d, and then you integrate it with respect to dt over t. If you don't like the principal value kernel 1 over t, replace it by any other kernel of your choice. You have another operator. If you don't like curves, you could average over surfaces. And that would give you yet another operator. And all of these operators, to varying extent, have been studied. It is just that in the plane and for the directional maximal operator, we have this clean, beautiful, and elegant characterization, which as of now is missing in higher dimensions.
Yeah, okay, good. Just one more question. So like you are doing harmonic analysis on RD, what about more general groups? What is that?
So I think I am certainly not the right expert for this, but there are there's been a lot of work done on compact Lie groups and also on nilpotent Lie groups. So I do not know exactly whether the directional operators have been studied in this context. Maximal operators definitely have been, but the directional operators have also been so there are two divergent directions. I know of work in maximal operators in the Lie group setting, And I know of directional operators in the setting of manifolds. So instead of an RD, you sort of restrict yourself to a manifold and you construct a directional maximal operator using geodesics instead of lines. And for example, authors like Christopher Sogg, Matt Blair, and their co-authors have a whole literature on Kakaya-like directional maximal operators on manifolds and the kinds of impact such operators have in the study of spectral properties of manifolds.
Thank you.
Yeah, so if there are no more questions, let us thank Professor Malabika once more for such a wonderful session. Thank you so much, Malabika. See you sometime here.
Thank you very much for having me. It was a pleasure. Thank you now.
Great, great.